In this video, we're going to look at differentiation and integration of a power series. Assume that a power series, summation n equals 0 to infinity, Cn x to the power of n, has radius of convergence r larger than 0, and defines a differentiable, which means continuous function, on the interval minus r to r. So here's the function, f of x, and we're representing this function by a power series. C sub 0 plus C sub 1 times x plus C2 x squared plus C3 x cubed, and so on. We can write this in summation notation, summation n equals 0 to infinity, C sub n, x to the power of n. Now, the whole idea is that this series can be differentiated term by term or integrated term by term, and a radius of convergence will remain the same as the original series. All right, let's differentiate. F prime of x is equal to, differentiate the first term, well, that's just a constant, its derivative is 0, and we're going to apply power rule to every one of these terms, so bring the power down and subtract 1 from the exponent. So we get C1 plus 2 times C2x plus 3 times C3 x squared, and so on. Now let's differentiate the summation, n equals 0 to infinity, differentiate x to the power of n with respect to n. C sub n is a constant, stays in the front, so we get C sub n times x to the n minus 1. All right, now notice that n equals 0 makes no contribution when you plug it in. So oftentimes we start this summation at n equals 1. So let's start it at n equals 1. All right, now let's integrate. Integral f of x dx, we're going to integrate every term. We always get a constant of integration coming out when we integrate, so let's put that first so we don't forget about it. C plus, integral of C0, we get C0x. Integral of C1x, we get C1 x squared divided by 2. Integral of C2x squared, we get C2 x to the power of 3 divided by 3, and so on. Now let's integrate the summation. Summation n equals 0 to infinity, C sub n. If we integrate x to the power of n, we reverse the power rule, we add 1 to the exponent and divide by the same. So we get x to the power of n plus 1 divided by n plus 1. And don't forget to add the constant of integration plus c. All right, so the key concept here is that the power series can be differentiated or integrated term by term, and the resulting series will have the same radius of convergence r as the original power series, summation n equals 0 to infinity, c sub n x to the power of n. However, convergence at endpoints may change. That is, the original power series may converge at x equals r, for example, the right endpoint, whereas a differentiated power series may diverge at the same endpoint at x equals r. So we have 4 different cases for the interval of convergence. We can have minus r to r, open brackets, that means we exclude both endpoints. The second case, we include the left endpoint and exclude the right endpoint. The third case, we exclude the left endpoint and we include the right endpoint. And the fourth case, we include both endpoints. Recall a closed bracket means include, and open bracket means exclude. All right, let's look at some examples. So here we have expressed the function f of x is equal to log of 1 plus x as a power series and find its radius of convergence. Exercise 1b, express log of 2 as a sum of an infinite series by using the result of exercise 1a. Now first notice that the derivative of log of 1 plus x is equal to 1 over 1 plus x. And we would like to find the power series representation of the function log of 1 plus x. Now we know that log of 1 plus x is simply the integral of 1 over 1 plus x dx. Because this is asking me find me a function whose derivative gives me 1 over 1 plus x. So log of 1 plus x is the antiderivative of 1 over 1 plus x. All right, now notice that the integrand happens to be the sum of a geometric series, and that's going to enable us to expand it out term by term and integrate term by term. So the whole idea is that the function for which we would like to find this power series is the integral of a sum of a geometric series. So let's expand this out. So we write this as 1 over 1 minus x. Minus x is a common ratio of this geometric series. And the first term is going to be 1. The next term, multiplied by the common ratio, we get minus x plus x squared minus x cubed, and so on. And integrate with respect to x. So log of 1 plus x is equal to, whenever we integrate, we get a constant of integration coming out. Let's put that first, c plus. And then integrate 1, we get x. Reversing the power rule, integrate minus x, we get minus x squared, divide by 2. Integrate x squared, and we get x to the power of 3, divide by 3. Minus x to the power of 4, divide by 4, and so on. We write this in compact notation. We get summation n equals 0 to infinity, minus 1 to the power of n, x to the power of n plus 1, divided by n plus 1. Now, we had to kind of recognize the pattern here. And to do that, if you want to check the result, for example, you can plug n equals 3, we get negative 1 to the power of 3, x to the power of 4 divided by 4, which is this term. So this term here is actually n equals 3. This term is n equals 2. And this is n equals 1. All right. So now we have the power series representation of log of 1 plus x. And the radius of convergence doesn't change. Is absolute value of x is less than 1. The radius of convergence, r, is equal to 1. Now let's find the constant of integration, c. So we can do that by plugging x equals 0 into both sides. So we have log of 1 plus x is equal to summation n equals 0 to infinity, minus 1 to the power of n, x to the power of n plus 1, divided by n plus 1, plus c. So this is the function, and this is the power series representation of this function. Our goal is to solve for the constant c. Let's plug x equals 0 into both sides. Plug x equals 0. We're going to get log of 1 plus x, 1 plus 0, is equal to summation n equals 0 to infinity, minus 1 to the power of n, times 0 to the power of n plus 1, divided by n plus 1, plus 0. Now all of these terms are going to be 0, so we get log of 1 is equal to, this is plus c, I'm sorry. So log of 1 is equal to 0 plus c. Now log of 1 is of course 0, so we solve for the constant, c is equal to 0. So that means that we have the power series representation of log of 1 plus x. This is equal to summation n equals 0 to infinity, minus 1 to the power of n, x to the power of n plus 1, divided by n plus 1. If we expand this out term by term, we get x minus x squared divided by 2, plus x cubed divided by 3, and so on. Now, we know that the original series 1 over 1 plus x is a geometric series, and it has a common ratio of minus x. So that's 1 over 1 minus x. So the common ratio r is equal to minus x. And it converges when absolute value of minus x is less than 1. That means when absolute value of x is less than 1, that means the radius of convergence, the radius of convergence of the original series is equal to 1. That, of course, means the radius of convergence of our new series is also the same, because we learned earlier that the radius of convergence does not change as a result of differentiation or integration. In this case, of course, it was integration. So the radius of convergence of the original series, which is a geometric series, is 1, and for that reason, the radius of convergence of our new series is also r is equal to 1. Now, part B is asking us to find log of 2. So we simply plug in x equals 1 into the series representation, power series representation of log of 1 plus x. So in part A, we found log of 1 plus x is equal to summation n equals 0 to infinity, minus 1 to the power of n, x to the power of n plus 1 divided by n plus 1. In expanded form, we get x minus x squared divided by 2 plus x cubed divided by 3 minus x to the power of 4 divided by 4 plus x to the power of 5 divided by 5 minus plus and so on. Let's plug x equals 1. We get log of 1 plus 1, which of course is 2, so let's just write it as log of 2. This is equal to summation n equals 0 to infinity minus 1 to the power of n times 1 to the power of n plus 1 divided by n plus 1, and this is equal to 1 minus 1 half, plugging x equals 1, plus 1/3 minus 1/4, and so on. So what we have shown is we have a series representation of log of 2. Log of 2 is equal to 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, and so on. Let me write this as minus, the next term is minus, and so on. And in compact notation, we can write this as n equals 0 to infinity, negative 1 to the power of n. Now, 1 to any power is just 1, right? So 1 to the power of n plus 1 is just 1. So the result is negative 1 to the power of n divided by n plus 1. Now, notice that this series, summation, n equals 0 to infinity, negative 1 to the power of n, this power series representation of log of 1 plus x converges at x equals 1. And that's what enables us to find log of 2. Converges at x equals 1. Now, let's show that it actually converges at x equals 1. So we get summation. Let's plug x equals 1 in here, and we get negative 1 to the power of n divided by, and plug x equals 1, and we get log of 2. Now the question is, how do we know that this is a convergent series? Well, we can apply the alternating series test, AST. The terms are decreasing. an is equal to 1 over n plus 1 is decreasing, and also the limit as n approaches infinity of a sub n is equal to 0. So by the alternating series test, this series converges. So what we have shown is that what we've really shown here is that we have a power series representation of log of 2 as this infinite series. And the more terms we have, the better our approximation of log of 2. All right, let's do a bit of review. So here we have the compact form of the differentiation and integration of the power series. So if we have the derivative of a sum, that's the sum of the derivative. That means you can bring the derivative inside the summation and apply the power rule. So we get n times Cn, x to the power of n minus 1. Similarly, we can integrate. Integral of a sum is sum of the integrals. So bring the integral inside the summation and integrate x to the power of n, reversing the power rule. So we get c sub n times x to the power of n plus 1 divided by n plus 1, summation n goes from 0 to infinity, and plus c. So power series can be differentiated or integrated term by term, and the resulting series has the same radius of convergence r as the original series. All right, thanks. I need to make a correction to this video. We're plugging x equals 1 into here. So this should be 1. 1 plus 1, that gives us log of 2. And this here is a series representation of log of 2. All right, thank you.